Hi, my name is Wyatt, and I'm going to be giving a brief presentation on my project relating to orbital mechanics. And as I'm talking about orbital mechanics, I want you to think about planets, and on the scale of solar systems. I'm not talking about molecules or anything like that. So my biggest goal in this project was to map orbits between objects. And what I mean by that is to have an object that's orbiting around one thing, and then shift its orbit to instead orbit around a second, separate thing. I thought this would be a nice, complicated problem that allowed me to dip my toes into orbital mechanics and kind of get a taste for how things work. So, in order to reach this goal, I had to get through a few stepping stones. First, I needed to build an animated model for orbits just so I could describe what's happening and see what was going on, basically creating the system. Second, I needed to learn how to describe transfer orbits, which basically just means anytime an orbit is changing shape. And then finally, I needed to learn how to design targeted orbits, which allow you to reach a certain point in space at a certain time by following an orbital path. The initial model coming out of this was relatively simple. All I had to do was account for the acceleration due to gravity based on the interactions between all the objects. So every single object would bring 3 second-order ODEs to the table describing its acceleration in the 3 Cartesian dimensions. And since an object in space is fully described by 6 parameters, this aligns up really nicely with having a system of 3 second-order ODEs. So this is how the model ended up coming out. You can just see how, given initial conditions for velocity and location, as well as the masses of the objects, it just describes forward in time what happens with their orbits. So I had a ton of fun messing around with this, and just seeing different shapes of orbits is definitely my favorite part of the project. Moving forward, I began to work with transfer orbits, and I started with a really simple case of the Hohmann orbit, or the Hohmann transfer, which is just changing from one circular orbit to a second circular orbit of a different radius around the same body. So these can be explicitly solved with Kepler's laws for orbital mechanics, which are just regular, simple algebra equations. And you just have to find an elliptical transfer orbit that connects the two pieces together. And it just involves a thrust at each change in order to actually change the shape of your orbit. So if we trace out the orbit that we described, you can see how it shows that elliptical transfer orbit between the two circular orbits, as you can see here. And in addition, you can do the same thing in reverse. Accelerate in the opposite direction, slow yourself down, and then return to that smaller, lower energy orbit near the planet. After describing the transfer orbits, I moved on to work with the targeting problem. This is a little more complicated and it involves hitting a certain location at a certain time. This is a type of boundary value problem because you have initial conditions for location, final conditions for location, and you have to connect the two through your ODE system by describing the velocity at the beginning. So whenever you're orbiting around a single body, this can be solved explicitly using Kepler's laws once again. And this has to do with a lot of really disgusting arguments with geometry and circles, and it makes some nasty equations, like really nasty equations. But at the end of the day, they're just equations, and it allowed me to plug in this new velocity that made these orbits intersect. The problem with this method of solution is that it's very rigid. It can't deal with orbits that have a weird shape, and it also can't work if there's more than one large mass contributing to acceleration. So not ideal for what I wanted from it. Instead, I wanted to deal with more complex systems, and so I needed a numerical method to solve. I decided to use the shooting method for boundary value problems, which is basically just a guess and check sort of deal. You pick some initial velocity, see where your object ends up at the target time, and then use route finding methods to direct that towards the target. So you're basically minimizing the function that describes the distance between your actual object and your target at that final time. And I used Broyden's method for route finding to solve for this, which is basically just 3D secant method, because I didn't need to solve for any derivatives that way. But with this, all the stuff that we've gathered together, I was finally able to finish out my problem, put it together, and describe an orbit changing between two objects. In this case, it basically just becomes a more complicated version of the transfer orbit we described earlier. In this case, the smaller orbit is the one around the planet, and then the larger orbit, where we're trying to intersect with that transfer orbit, is just to make the object intersect with the planet, which can be solved with the targeting method that we put together. And finally, putting a little bit of thrust allows that orbit to enter that circular pattern that we wanted it to reach. And yeah, that's how it all kind of came together. So, since this was a short-term project, there's obviously a ton of room for improvement. One thing in particular that I didn't consider was fuel limits. I assumed that any sort of acceleration would be allowed for my model, and didn't make any attempts to minimize the amount of fuel needed for it, which obviously in real life that would be an incredibly important parameter to try and minimize. Second, I didn't consider different paths towards a target. The method for root solving that I used only converges on local roots. So if there's multiple paths that could lead to a target, I didn't make any attempts to determine which one would be better than another. And finally, coding efficiency was an issue with this, especially in the roots finding method. I had to call ODE45 for every single iteration as we're trying to find the proper path. And so considering that the number of iterations for this process was sometimes over 2,000, there's quite a bit of time spent just waiting for this code to run. So ultimately, definitely some room for improvement, but that's sort of the path that I had, my own trajectory through orbital mechanics, and thank you so much for listening to my presentation.